Hi everyone, welcome back to MATC58. We have now successfully done most of the material related to difference equations that we're going to be covering in terms of mathematical theory. Instead, for the next couple lectures, we're going to talk about trying to apply these mathematical techniques to real biological examples. And I thought we'd get started with one that is highly topical. Let's talk about epidemics, especially epidemics concerning a novel disease where no one has immunity to begin with. So for today, let's give a couple objectives. So objectives. One, we're going to apply difference equations to modeling epidemics. To modeling epidemics. Sorry. But more than that, we're also going to be seeing understanding how to construct a model. So obviously, I could just give you a model of an epidemic, and then we can analyze that, which is sort of what we've been doing with the biological examples in the last several weeks. But today, we're going to spend some time and try to step-by-step construct a model and see what happens. So let's understand what it means to construct a model, how to construct a model, and some of the things that can go wrong. Construct a model. And lastly, we're going to see what can go wrong with modeling. See what can go wrong. As I mentioned at the very beginning of class, all models are wrong, some are useful. What can go wrong with modeling? I think I misspelled with. Okay, so let's start by putting some assumptions on the model. So we're going to be talking about an epidemic, and many epidemics spread when people come into contact with each other, right? So let's say assumption 1. I'm going to call this 1A actually, because we're going to modify this in a moment. Assumption 1A. People randomly have contact events with each other. Have contact events with each other. And by randomly, I mean that they can contact anyone else in their population. So we're not going to put any sort of additional structure on the contact events. And let's go ahead and give assumption 1B. So assumption 1B, which is that when an infected person contacts a susceptible person, there's some chance of infection. So when an infected person let's use individual. I think that's more standard. Individual contacts a susceptible person. So these are the S and I in the SIR model. Contacts a susceptible person. There is some chance of infection. There is some chance of infection. And I'm going to combine these two assumptions together into just assumption 1. So assumption Assumption 1. So each infected person infects beta other individuals in time step. So each infected person infects beta other individuals in time step. So we're basically lumping both of those assumptions together into one bigger assumption that's going to be a little bit easier to characterize. Okay, so if we just have these assumptions, well, let's try to build a model off of just this one assumption. So we have some I sub t, which is the number of infected individuals, and that's going to be equal to infected individuals stay infected, since we haven't described otherwise. So I sub t plus beta times I sub t, since that's the number of additional individuals that they infect over a time step. So where I sub t is number of infected. Number infected at time t. Sorry, let me at time t. Okay, so what happens now? Well, we can rewrite this pretty easily. So this is I sub t is equal to I sub t, 1 plus beta I sub t. 1 plus beta I sub t. Well, then we know how to solve this. This is just a very simple linear first order difference equation. So this implies that I sub t, that's I sub t plus 1. I sub t is just equal to 1 plus beta to the tth power times I naught. So exponential. Okay, so this here is just exponential growth. And that looks something like that. This is t, and this is I sub t. So now this is a little bit unrealistic, because we don't actually have infinite people to infect, and so at some point this clearly has to level off. And so we can encode that into another assumption. So we have this one model, which is we just had this one fact that each person infects beta other individuals in a time step, and if we only use that one fact in our model, then all of a sudden we get exponential growth. And this might make sense as a first order approximation, but obviously it can't hold up, because in real populations we don't have, we can't just get exponential growth, has to hit a ceiling somewhere. So let's encode that. So this is assumption 2, which is there is a total population size. Total population size, let's call it n. Population size n, which is equal to I sub t plus s sub t, where s is the number of susceptible individuals, where s is the number of susceptible individuals. Okay. So what happens when we do have this assumption in place? Well, when we do this, we have to modify assumption 1 slightly. So let's put this down. Modified assumption 1, which is each individual still has beta contacts. beta contacts per individual. But when you contact another infected individual, that doesn't have an effect. But infected contacts have no effect. And so if infected contacts have no effect, so if the contacts are random, then we have some probability of getting a susceptible individual are random. Then we get a S over N probability of infection. Probability of infection per contact. Because with probability S over N, you actually get someone who is susceptible, and so you can infect them. And so now with this new model, with this new assumption, we can put in a slightly different model. So this is going to be model 2. Okay, so what do we know? We know that n is equal to I sub t plus s sub t, and we know that I sub t is equal to I sub t plus, well, how many new infected individuals are we get? So we have beta contacts per individual. We have beta contacts per individual. We have I sub t infected individuals, and then we multiply it by s over n for the probability that you get an infection out of that contact. And s sub t is going to be pretty similar, so we're going to lose however many individuals from our susceptible population because they become infected individuals in the time step. Okay, so it turns out that we can combine these things together, and because n is equal to I sub t plus s sub t, we can substitute that in. So this implies that s sub t is equal to n minus I sub t, and so we can combine all these things together, and we can characterize it with just a single variable, so just number infected, because that's just, you can compute the number of susceptibilities by subtracting the number infected from your total population size, which is a constant. So I sub t is equal to I sub t plus, let's see, this is beta I sub t n minus I sub t, since that's what substituting in for s sub t, over n. And we also get that then I sub t is equal to I sub t plus, let's say this is, I'm going to rewrite it a little bit, beta I sub t minus beta I sub t squared divided by n. And let's rewrite it even a little bit more. So then I is equal to I sub t equal to 1 plus beta times I sub t times 1 minus beta I sub t divided by n times 1 plus beta. And I'm rewriting it this way for a very particular reason, which is then we can do a change of variables. So let's change variables. So then let's say x sub t is equal to beta over n times 1 plus beta times I sub t, which implies that, of course, I sub t is equal to n times 1 plus beta over beta times x sub t. And when we do this change of variables, what we get is that n times 1 plus beta over beta times x sub t is equal to 1 plus beta times n times 1 plus beta over beta times x sub t times 1 minus x sub t. And we can divide out by both sides. And so this implies that x sub t is equal to 1 plus beta times x sub t times 1 minus x sub t. So now you should recognize this. If you replace this 1 plus beta here with some other parameter r, this entire thing is just a discrete logistic equation. So this is just the discrete logistic equation, which we studied at length in the last couple lectures. But now, at this point, you should be thinking to yourself, this seems a little bit odd, because we know that we already studied the discrete logistic equation, and we know that there are the equation has cycles and chaotic behavior for r is greater than 3. On the other hand, we also know that here, the number of infected individuals is growing over time. So it's growing monotonically, because once you've become infected, well, you can't, there's no mechanism for you to not become infected in our model. And so the number of people who should be, so I sub t should only be growing bigger. Let me actually put in an image of the discrete logistic equation just to show you that things go horribly, horribly wrong when you try to use this model to model epidemics. I'm going to paste in an image from Wikipedia. So this is just the bifurcation diagram for the discrete logistic equation. Why is my pasting not working? Come on. Ah, there. Okay, so this is from Wikipedia. Let me just specify this. Wikipedia for discrete logistic equation. And this is a bifurcation diagram. Bifurcation diagram. So you note that when r is greater than 3, then all of a sudden you have these cycles, and when r is greater than around 3.1, around this region here, you get super chaotic behavior, which is not good. So remember, we have some chaotic behavior and cycles. But of course, if your epidemic spreads, like if everyone who's infected infects another 5 people, well, you're not going to get like weird back and forth behavior in real life. So what gives? What has gone wrong? So let me be actually keep on zooming. This is for x sub t plus 1 is equal to r times x sub t 1 minus x sub t, where I've just listed out all the stable equilibria cycles and 2 cycles, as well as things like chaotic behavior. Okay, so at this point, you should understand, well, simply because you can write down a model doesn't mean that it's a good model. So let's take a moment and step back and try to understand what is going wrong here. So we started off with some model where you have monotonic behavior. So this monotonically grows, right? So that monotonically grows, but then all of a sudden we know that this thing doesn't. This thing is chaotic. And so this is a breakdown in some of the model assumptions, as well as the fact that we're using a difference equation. So what's going on here is that even though this is monotonically growing, the number of infected individuals is constantly growing and doesn't decrease according to our model parameters, when we write it in, things don't always work out that way. So more precisely, let's take a concrete example. So suppose that I sub t is equal to n minus 1. So if I sub t is equal to n minus 1, so like if most of our individuals are infected, well, then what happens is I sub t is equal to n minus 1 plus beta times n minus 1 divided by n. And so if beta is greater than 3, then let's actually, if beta is greater than 3, then I sub t plus 1 is greater than n, which is clearly impossible. So our problem is assuming beta s over n infections per individual. Because when we actually assume that there are that many infections per individual in the time step, sometimes what happens is your overall time increases. And so then if I sub t is bigger than n, well, that's super bad because that means that s sub t is a negative number. So we just assume that we have a negative number of susceptible individuals when we do that. And so this is one case where the model breaks down, and because we're using a difference equation, and so you can't continuously go up to maximum infected individuals. Instead, sometimes you accidentally jump over your population size, and then the model forces you then to have a negative number of susceptible individuals, which is not physical. So this is still a model that you can use if you understand these limitations. Unfortunately, these limitations are really quite strong. And this is a really good illustration of what can go wrong when you just write down the model and assume that it's going to work out. Because looking at this model, you might think, oh, well, if every individual infects 2.5 other individuals, well, then you get chaotic behavior going back and forth. But then if you take a step back and think about the assumptions that infected individuals are never dropping out of the population, this doesn't make sense anymore. Okay, but anyway, let's press onward and add some more conditions now that we've gotten a sense that things can go wrong. But if we're careful, maybe we can still get away with something. So I'm now going to introduce the SIR model. So this is going to be the basic SIR model. There are many fancier augmented versions of it, one of which we're going to talk about. Oh, what just happened? Okay. See, so this is assumption 3. Assumption 3, so individuals recover with some probability. Recover with probability gamma. And we're going to assume for now that there are no deaths. So individuals recover, and then they're no longer infected. So this is going to be, and I'm going to draw this in compartments. So we have S for susceptible individuals, we have I for infected individuals, and we have R for recovered individuals. And for the purposes of this model, we're going to assume that once you've recovered, you can't become infected again. There are other models where you don't make that assumption, but here we have a beta I over n, what was our probability again? So this is going to be beta I over n, yeah, so beta I over n probability of becoming infected, and we also had a gamma probability of recovering. And so this here is the basic SIR model. Okay, and this captures some kinds of fast-spreading diseases. The effective spread rate is, in this case, slower because recovered individuals are not infectious. And so that's actually kind of important. In the previous case, you assumed that when someone became infected, they were infected forever and kept on infecting people. And that's true of some diseases, but with other diseases, the spread actually does slow down a little bit because once someone is recovered, well, then they're no longer infectious, and also if an infected person contacts a recovered person, they don't end up infecting them. So let's write down the equations for this particular model, which are going to be similar to the previous one, but now we're going to have an additional term, R sub t. So let's start out. So we have S sub t plus 1 is equal to S sub t minus beta over n times I sub t times S sub t. Okay, so that's pretty straightforward. So nothing changes with the S equation. But for our I equation, we do have a difference. So I sub t plus 1 is going to be equal to I sub t. So you have the number of individuals, but then with gamma probability, you remove the individual from the infected population. But then we also add in the new infected individuals, I sub t times S sub t. And then we have a third variable, so R sub t plus 1, which is equal to R sub t plus gamma times I sub t. So at every time step, some number of individuals are recovering. And as a note, we also know that n is equal to S sub t plus I sub t plus R sub t, because that's just our total population size. So we can let R sub t be equal to n minus S sub t minus I sub t. And then we'll note that it doesn't have any direct influence on S sub t and I sub t, and so we can reduce this into a system of two equations. So in the previous case, we had two equations that are reduced to one equation. In this case, we are reducing 3 to 2, and so we end up with, let's see, S sub t plus 1 is going to be equal to S sub t minus beta over n I sub t minus S sub t, and I sub t plus 1 is going to be equal to I sub t times 1 minus gamma plus beta over n I sub t times S sub t. Okay? And now we want to solve for equilibria. So let's see, solving for equilibria. So we're solving for equilibria. Well, what do we get? We get that S bar is equal to S bar minus beta over n times I bar times S bar, and we have I bar is equal to I bar times 1 minus gamma plus beta over n I bar S bar. Well, when we put all these things together, what we get is that 0 is equal to minus beta over n times I bar times S bar, and gamma I bar is equal to beta over n times I bar S bar. And the conclusion from all this is that I bar is equal to 0, and there are no constraints on S bar, and R bar is equal to n minus S bar. And so what does this mean? So this means that the only equilibria are when there are no infected. So we, if you're at an equilibrium, basically because if you have any infected individuals, well, then the number of infected individuals is going to change, and so are the number of recovered individuals. Because, well, if you have any infected individuals, well, it's going to decrease the number as people recover. Or it's going to increase in number as it infects more of the susceptible people. And so so long as you have any infected individuals, in the next time step, you'll still have a few infected individuals, even if that number is decreasing. Let me go ahead and so draw out heuristically roughly what this looks like. So for a particular trajectory, so let's say this is time, and this is population. And so you might have something like the total sum has to all sum up to the total population size. So this is going to be n. But they can, if we start out with susceptible individuals, so you might have something like your infection rate is going to go up. Let's do that in red. It's going to go up. As the infection rate goes up, your uninfected, your susceptible population goes down. So let's list. But as the infection rate goes up, it tops out at some point. So it might, yeah, come on. So it tops out and then goes back down to 0. And then you have, because as the infected goes, you start recovering. So you have some recovery curve down here. And you have, let's see if I can draw this reasonably. So this is our S sub t, this is our R sub t, and this is our I sub t. And so this is vaguely what it looks like. Rough trajectory, example trajectory, example trajectory. And so this is in some sense not very interesting. Like, we have a model, and yes, it does sometimes tell us something useful, which is that the only equilibria are when there aren't any infected individuals. So either everyone's recovered or like it dies out for some other reason. But it turns out that if you add some other dynamics, we get much more interesting behavior. So this is in some sense not super interesting behavior, though you do see the infection curve, which you've probably heard about a lot in the news lately. But for the purposes of this class, let's go ahead and throw in another assumption, which turns out to give it a much more interesting equilibria and solutions, and then we'll analyze the stability of those. So let's put this down as assumption 4, and this is going to include something called vital dynamics, by which we mean life and death. So individuals are going to born and die. So we're going to do this in a sort of weird way to let individuals die. But we want to keep constant population. And so when someone dies, in order to keep constant population, you also have to have a child be born at exactly during the same time step. So this is a sort of weird assumption because you're sort of linking together birth and death, but it's necessary if you want to have this constant population size, which is going to make the analysis a lot easier. In the general case, for an even more complicated model, you might let the total size of the population also shift, but we're not going to do that for this model. So it turns out that when you do that, you get this weird sort of condition, which is that individuals die / are reborn, because when an individual dies, a new child has to be born to replace them, or you wouldn't have constant population size, with some probability. Well, let's call that probability B. And whenever an individual is born, they're born susceptible, or born susceptible. So because they clearly aren't recovered since they've never had the disease, and we're going to assume that they aren't born with the disease. Okay, and this has, there are some diseases that this sort of model works well for, and often these are things like childhood diseases. Well, let me actually separate these a little bit, just so, yeah. So these are things like childhood diseases like measles, chickenpox, etc. So all the things you get vaccines for when you're a kid. Or many of those, at least. But yeah, so this weird assumption allows us to, weird assumption allows constant population size. Constant population size n. Okay, so now let's revise our SIR model with this additional B parameter. So again, we have S, we have our I, and we have our R compartments. And so we start out with our regular thing. So we have our beta I over n probability that you go from susceptible to infected. So that includes both the probability of contacts and the probability that when you contact them that you get infected. That you've contacted an infected individual. There's a pairing of an infected and susceptible individual. You have some gamma, which is the probability of recovery. And then we also have some probabilities, which we're going to call B, of dying and being reborn as a susceptible individual. And we also have the self loop, since susceptible people can also die and reborn as susceptible. But it doesn't really make a difference in this model because that's just a constant. So this is not no effect. This particular b has no effect. Okay, so these are transition probabilities for an individual between these different states. Okay, so now let's write out our equations again. So we have, let's see, s sub t plus 1 is going to be equal to s sub t minus beta over n I sub t s sub t. So this is the usual thing. But we're also going to get an additional source of susceptible individuals. And this is going to be b times I sub t plus r sub t. Okay? And we have our I sub t plus 1, which is going to be equal to I sub t. And how many people are going to leave the infected category? Well, the probability of leaving the infected category is 1 minus gamma for recovery, or minus b for dying and being reborn. Plus, of course, the people who are introduced, beta over n, I sub t, s sub t. So those are the newly infected. And we also have r sub t plus 1 is going to be equal to r sub t times 1 minus b plus gamma times I sub t. So now you might be asking why this thing doesn't show up anywhere. Well, the reason for that is because, in effect, that would be a minus b s sub t plus b s sub t, since b s sub t are leaving and b s sub t are arriving. Because of that, that's a self loop. So we can just ignore that part. Okay, and of course we can again reduce to a system of two equations. So use n is equal, let's say use r is equal to n minus I sub t minus s sub t. Let's actually do it in a different order. Let's do s sub t, I sub t, just so we stay in the SIR order. Minus s sub t minus I sub t. And that gives us a system of two equations. So we get s sub t plus 1 is equal to s sub t minus beta over n I sub t s sub t plus b times n minus s sub t. And we get that I sub t plus 1 is equal to I sub t times 1 minus gamma minus b plus beta over n I sub t s sub t. Okay, so we again have two equations, and again we can solve for the equilibria by setting the t plus 1 state variables equal to the t state variables. So solve for equilibria. And I'm not going to actually solve this by hand, since you guys know how to do that now. But instead I'm just going to list out the equilibria that you get. So 1, you get s bar is equal to n, and I bar is equal to 0. So this is often called the disease-free equilibrium. So this is the equilibrium that happens when the disease dies out for some reason or another. So in this equilibrium, no one is infected, and everyone is susceptible, because if everyone was recovered from the disease, eventually all those recovered people would die off, and then everyone becomes susceptible. All reborn children would be susceptible again. The other equilibrium, and this is a little bit more interesting, and the reason why we added this condition, which is we have s bar is equal to n times gamma plus b over beta, and I bar is equal to bn times beta minus gamma plus b divided by beta times gamma plus b. And this is what's called the endemic equilibrium. And note that this is positive if beta is greater than gamma plus b. So what is this? This means that at this equilibrium, you have some constant proportion of individuals that are susceptible and some constant proportion that are infected, and also some constant proportion that are recovered. And so the disease is endemic to the population in that it never disappears, but it never disappears, but also doesn't take over the entire thing. So how do we do a stability analysis? Well, this is a system of first-order equations, system of first-order nonlinear equations, and so we have to use the Jacobian. So Jacobian matrix. So that would be J of Si is equal to, what you do is you take the partial derivatives of listing. So we need to take partial derivatives, and when we do that, what we get is 1 minus b minus beta over n times I, minus beta over n times s, beta over n times I, and 1 minus gamma minus b plus beta over n times s. So you should take some time and verify these steps individually if you're not comfortable doing partial derivatives, since this is something I expect you to be able to do, and so I'm not going to walk through it every single time. So now, well, there are different possibilities. So at the disease-free equilibrium, let's see if that is stable. So basically, is it stable for there to be no disease in the system? So J of n0 is equal to 1 minus b minus beta 0 and 1 minus gamma minus b plus beta. Okay, so eigenvalues, lambda 1 is equal to 1 minus b, and lambda 2 is equal to 1 minus gamma minus b plus beta. And so we assume that b is greater than 0, so there is some birth and death rate. So that means that our first eigenvalue is between 0 and 1, and so clearly that means, actually, I should make that clear, b is greater than 0 and less than 1. So you can't have more people, you can't have a greater than 1 probability of dying and being reborn. But so because of that, our lambda 1 has modulus less than 1, and therefore all we need for it to be locally asymptotically stable is if the lambda 2 also has modulus less than 1. So locally asymptotically stable if beta is less than gamma plus b. Or equivalently, if beta over gamma plus b is less than 1. Okay, so we have some condition on the local asymptotic stability of the disease-free equilibrium. So is it stable for the system to have no disease? And that depends on this number beta over gamma plus b. So let's go ahead and give that a name, which we've seen this name used before, and it's used in basically the same setting. So we're going to define the basic reproduction number. And we're going to call it R naught is equal to beta over gamma plus b. Now, what does this basic reproduction number mean? So let's try to interpret it. So note, so at each time interval, we have some probability of an infected individual either recovering or dying. At each time interval, at each time step, probability gamma plus b of infected individual either recovering or dying. So either recovering or dying. So if in each time interval you have a gamma plus b probability of either recovering or dying, how long will an individual remain infectious? Well, if at each time interval you have a 1/2 probability of recovering or dying, then on average it takes you 2 time steps for you to either recover or die. And so just 1 over gamma plus beta. So in expectation, sorry. They will remain infectious for one over gamma plus beta. 1 over gamma plus beta time. Okay, so 1 over gamma plus beta is the amount of time they remain infectious, and on average, infect beta individuals in each beta individuals each time step if the number of susceptible individuals is close to 1. If S over n is close to 1. So therefore, R naught equal to beta over gamma plus b over gamma plus b is the expected number. The expected number of individuals infected by an infectious person over their time being infected. Expected number of new infections caused by an infected individual. An infected individual. If, of course, S over n is close to 1. And so when you introduce a disease into a population, so if there's some very small number, then most individuals are susceptible and that's close to 1. And so this is the expected number of new infections when there are very, very few infected individuals. And you can assume that most contacts result in infection. So this corresponds to the expected number of new infections when a disease is introduced into the system and no one has any immunity. And so if R naught is greater than 1, disease-free equilibrium is unstable. So the disease is unlikely to die out on its own. If R naught is less than 1, disease-free equilibrium is locally asymptotically stable. And recall that if R naught is less than 1, you also don't have the Euler equilibrium, because the Euler equilibrium only exists when R naught is greater than 1, since we know that it's positive only if beta is greater than gamma plus b, which is the same as R naught being greater than 1. Okay, so this allows us to characterize most of this equation. We still don't know about the stability behavior of the other equilibrium, but let's go ahead and actually I'm going to go ahead and give you a couple example R naughts. So this is table 2.2 in your book. And so something like smallpox has R naught is about 3 to 5. Measles has R naught about 12 to 13, and so that's quite infectious. And chickenpox has R naught about 9 to 10. So these are empirical results from various epidemics that we've seen in the history of like smallpox, measles, and chickenpox. Okay. So that was our analysis of at the disease-free equilibrium. Let's do a very quick analysis of the endemic equilibrium. Endemic equilibrium, which is S bar is equal to n times gamma plus b divided by beta, and I bar is equal to bn times beta minus gamma plus b divided by beta times gamma plus b. And then you can compute the Jacobian. I'm not going to do it by hand. The Jacobian is just an equal to 1 minus b r naught and minus beta over r naught, and b times r naught minus 1 and 1, where r naught is greater than 1, of course, because we only care about the positive case. So for simplicity, we're going to assume that the trace is positive. The trace of j is equal to 2 minus b r naught is greater than or equal to 0, or non-negative at least. And also, we know that the determinant of j is equal to 1 minus b r naught plus beta b times 1 minus 1 over r naught. Okay, and then we can use the jury conditions. So then by theorem 2.10, so these are the jury conditions, blend, let me make this, the theorem 2.10 jury conditions are as follows. So what we need to show, what we need in order to get local stability is 2 minus b r naught is less than 2 minus b r naught plus beta b times 1 minus 1 over r naught is less than 2, which is of course entirely equivalent to saying that 0 is less than beta b times 1 minus 1 over r naught is less than b r naught. But of course we know that r naught is greater than 1, which is greater than beta times 1 minus 1 over r naught, because that's negative. So jury conditions satisfied. So therefore, the endemic equilibrium exists because r naught is greater than 1 and is locally asymptotically stable if r naught, if r naught is greater than 1 and r naught is less than or equal to 2 over b. So now, in other cases, we've only analyzed it for this very specific case where r naught is less than or equal to 2 over b. In other cases, it might be stable or unstable, or it might even be chaotic, depending on what the model parameters. But those are a little bit harder to analyze, and we're not going to worry about that for today. Instead, we'll just note that under certain conditions, you have this endemic disease in your population, which corresponds to the real behavior of measles just being part of the population when in the absence of vaccines. Now, in other cases, we might want to include things like vaccine models, or we might want, so for example, if you're dealing with some novel coronavirus, maybe you want to model what happens if you vaccinate people. Or you might wonder, well, what happens if when people recover, they aren't immune? Well, then can we model that? And yes, so that will actually be one of your breakout session problems, will be the SIS model, where after someone's infected, they recover but become susceptible to being infected again. So that will be, so that basically ends today's lecture on the SIR model. Unlike some of the previous videos, I'm not going to break this out into two different videos, one with theory and one with application, because this is entirely an application video. And so we've just spent the entire time on discussing this one application of linear difference equations. Well, thank you very much, and I will see you in the next video.